Okay, so next up is now we're going to move into addition reactions. Addition reactions are going to start with acid-base reactions, and then we're going to add another step after the fact. So we'll see how this goes, and let's get started. Okay, so an addition reaction, recall that an addition reaction, of course, starts with the breaking of a pi bond. And so let's take, I don't know, let's just do 2-butene. And we're going to react it with HBr. Right? HBr is a strong acid, right? We covered that in our strong acids, or all that kind of stuff. We know that this hydrogen is easily removed because Br minus is such a stable conjugate base, right? So we have our acid and we have our base. Now we always start our reaction from the base position, right? And so the base position is our pi bond. We don't have any lone pairs to use as a base here, so we're using the electrons from the pi bond. Those electrons are going to come get that hydrogen. We're going to make a bond to the hydrogen. We're going to break the hydrogen-bromine bond, right? So once again, we're doing a Bronsted-Lowry acid-base reaction. We are making a sigma bond at the same time that we're breaking a sigma bond. And because we're using a pi bond, this is how we generate carbocations. So I'm going to put the hydrogen on this carbon and a positive charge there. It doesn't matter. You can obviously add, or in this case, you can add the hydrogen to carbon 2 and put the carbocation on carbon 3. That would also work. And we get Br minus. Okay, so this is a pretty standard Bronsted-Lowry acid-base reaction. And if you don't think about it too hard, it makes perfect sense, right? We made a sigma bond, we broke a sigma bond, everything's great. Now, but think about what else we've learned this week, right? One of the ideas that we really hit hard was this idea that the reaction always goes to the most stable conjugate base, right? And so the question is, have we done that? Is this reaction creating Br minus and a carbocation, is the right side of this reaction, the product side of this reaction, more stable than two neutral compounds, 2-butene and HBr? Or am I trying to pull a fast one on you? Am I just saying, yeah, no, it's fine. This time it will happen that way. And the answer is no. Like really, in most cases, this reaction is not going to occur, right? The stronger acid is the carbocation. The stronger base is Br minus compared to an alkene like this. And so instead, we actually don't have this equilibrium favors the starting materials. But if you mix 2-butene and HBr, they don't just sit there and stare at each other. You actually get a different product. And the reason is that when this reaction happens, and it doesn't happen all the time, it doesn't happen incredibly often, right? But when this reaction happens, it doesn't stop here. It keeps going, right? And of course, what's going to happen is we have a negative charge and a positive charge. These two things are going to attract each other. So now we have a conjugate base here and we have a conjugate acid here. Acids and bases can, of course, react. We're going to start from our base, as always. We're going to take that negative charge and bring it to the positive charge, right? So this is a two-step reaction. Step one, form the carbocation. Right? And we form the carbocation through a Bronsted-Lowry acid-base reaction, right? We've talked about how we do this, and we've talked before about how carbocations are really unstable. They're not favored, and they're not something that we really want to stick around or use in our reactions. And so what happens is, of course, immediately that carbocation says, well, I need something to react with because this is not a good situation, right? This conjugate acid here is not a good situation. And so it's immediately going to find something to react to. And it has a choice. The Br minus can take the hydrogen off and go straight back to 2-butene and HBr, right? And that happens for sure, but that's not the interesting thing. What's more interesting is if the Br minus gets attracted directly to the carbocation and we end up with a new sigma bond where that bromine is now attached to carbon 2. right? And so we make 2-bromobutane as our product. And overall, of course, you'll notice that what we've done is we've broken a pi bond, right? 1 pi bond broken, 2 sigma bonds made, right? So we make a sigma bond here. The pi bond makes a sigma bond with the hydrogen. And then in step 2, we react the carbocation. In step 2, the bromine comes in and makes another sigma bond. And so overall, an addition reaction, right? Whoops, oh man, pretend I didn't do that. An addition reaction, which we talked about when we did our reaction classification, right? An addition reaction does these two things. We break a pi bond and we make 2 sigma bonds. And this is a pretty classic way for addition reactions to take place, right? We're going to make a carbocation and then we're going to have our conjugate base come back in and react with that carbocation. Now, this works with a whole bunch of different conjugate bases. So let's look at, I'm just going to keep using 2-butene because it's a nice, easy substrate where we don't have to worry about too much here. 2-butene plus HCl. What would you predict is going to happen? Well, what's going to happen is our pi bond is going to come, attack that hydrogen, break the hydrogen-chlorine bond, and we're going to make a carbocation. This time I'm going to go the other way. But again, if you draw your carbocation on carbon 2 instead of on carbon 3, totally fine, right? You'll get the same product, more or less. It'll just be flipped over. Right. Cl minus comes back in, attacks that carbocation, and we get 2-chlorobutane, right? You can do the same thing with HF. The steps will be exactly the same. You will get 2-fluorobutane as your product. Okay. Now, what happens if we take 2-butene and react it with, oops, yeah, this will work, and react it with sulfuric acid and water? Now, at first glance, this looks pretty much the same, right? We have acid, we have an alkene, and so we would expect the first thing that's going to happen is we're going to make a carbocation, right? And you'd be right, right? The first thing that's going to happen is H2SO4 is really, if you react H2SO4 and H2O, what you're really making is H3O plus, right? That's the conjugate acid of H2O. And H3O plus we can consider as H plus and H2O, right? Because if we react it with H plus, we're going to generate the conjugate base H2O. So really, when we see H2SO4 in a reaction, we can just cross it out and draw an H plus over it. Because H2SO4 really will react with water first. Where's my mouse? H2SO4 always just reacts with water first and then becomes H plus, and then we use that in the reaction. We don't ever really use the conjugate base of H2SO4 to do anything because it's just so unreactive. H2SO4 is such a strong acid that HSO4 minus is just completely unreactive and completely stable. So instead, water is going to be more reactive than the conjugate base of sulfuric acid, so we use water as our base. Okay, so now we've got H plus and H2O in there. Let's have our pi bond, whoops, come back here. Let's have our pi bond attack H plus. And now we don't have a negative charge, but we have water, which is going to be our base in step 2. Water is going to come in and add to that. And so now we'll have the same result where we've made a new sigma bond with the carbocation. Fortunately, we have a positively charged oxygen now, which isn't going to be terribly stable. And so what that's going to do is it's going to lose H plus. So we're going to minus H plus. And what probably happens is another molecule of water comes, takes that OH2 plus and turns it into an OH. Right? So probably what's happening is we're adding water and creating H3O plus again, which then of course will just feed back into the reaction at the beginning here. We'll have H3O plus, which is just H plus and H2O, and the reaction starts over. So this is a little bit more complex than the HCl or HBr example, but the idea is the same. Step 1, generate the carbocation. Step 2, have your base come attack, have that conjugate base. What's the conjugate base of H3O plus? H2O. Have that conjugate base attack there. We have an extra step where we got to get rid of a hydrogen, get rid of a proton, an H plus, in order to get back to a neutral compound here. But that extra step is just a Bronsted-Lowry acid-base reaction, right? Where we have our acid, the positive charge here. We have our base, which is H2O, and then we have a conjugate acid, H3O plus, and a conjugate base, which is this alcohol. So that's basically 4 different addition reactions that we just did. We took 2-butene and we added to it HBr, HCl, HF, and H2SO4 with water. Right? So you can go through those and kind of figure out how they work. The mechanism is going to be the same every time. Step 1, make the carbocation, Bronsted acid-base reaction. Step 2, react the carbocation. Have your conjugate base come attack that carbocation. Right? So in those senses, it's kind of the same mechanism 4 different times. You're just swapping out what is your conjugate base in each case. Right? We're going to talk a little bit more about the carbocation in the next video, and I think that will get us through this week. So we'll see you in the next one.